We are Kemi, Lauren, and Ariella, and this is our senior design project, ChitoAid. Diabetic foot ulcers are a highly prevalent condition that significantly affect the life quality of millions of diabetics. 10.2% of Americans have diabetes, 15% of diabetics develop diabetic foot ulcers, and 85% of all lower limb amputations are a result of diabetic foot ulcers, which shows how common this issue is. Ulcers occur as a result of chronic wounds or high pressure on the foot. Healing is especially difficult for diabetic foot ulcers that are infected and lead to biofilm buildup because diabetics have poor peripheral circulation and neuropathy from increased blood glucose that damages vasculature, and these are the issues that ChitoAid addresses. Currently, there isn't an ideal mode of care to treat ulcers and avoid infection. Clinicians tend to use either a very simple or complex bandage model, but do not have a streamlined method of choosing bandages. Our solution to diabetic foot ulcers is ChitoAid, and it includes the three most important features to antimicrobial bandages that clinicians look for. It is based of electrospun chitosan that intrinsically allows for accelerated skin regeneration and an antimicrobial surface, which takes care of the slow-healing chronic wound. It has Zwitterionic nanoparticles that are antibacterial and eliminate biofilm formation. And it has an integrated pH detector of phenol red nanoparticles that work as a visual indicator of infection for those who have neuropathy and can't see or feel when they have an infection. Looking at current modes of care, gauze of Vaseline is most commonly used, but is a very simple model that doesn't control for bacterial growth. Silver alginate is more advanced and antimicrobial, but silver alginate may not be biocompatible as it may cause cytotoxicity. Chromogram is also more advanced, but it does not account for antifouling or have an infection indicator. ChitoAid is antimicrobial, antifouling, biocompatible, skin regenerative, and includes a unique infection indicator to let clinicians know of a bacterial infection according to a pH sensor. As for cost, ChitoAid is the most expensive option at $8.57 for a 1x3-inch bandage mat, assuming that facilities have an electrospinner, which could possibly add on to costs. Compared to the other bandages, it is more expensive for a smaller amount. However, clinicians have assured us that because our bandage includes the sophisticated features of being antibacterial and including an indicator of bacterial infection, the price is worthwhile for effective results.
This is an image overview of our bandage. Closest to the foot ulcer, we have a layer of nanoparticles that include the Zwitterionic nanoparticles to fight infection and the phenol red nanoparticles to detect the infection. Underneath that is a layer of chitosan PEO fibers. PEO is a base polymer and used for mechanical strength. This layer helps with skin regeneration and is the basis of our bandage. Finally, we have a thin base layer of PEO which prevents the bandage from sticking to the packaging, and this faces the outside environment. There are three areas of the project which need evaluation. First and foremost, at the top of the triangle is our electrospun chitosan fibers. This is the base of our material, and we will perform both instron and FTIR spectroscopy tests on this. pH testing will be conducted for the phenol red nanoparticles and FTIR spectroscopy on the Zwitterionic nanoparticles. When our final product is assembled, we will test the whole device with cytotoxicity and bacterial testing. Diving into the first aspect of our mat, the chitosan base, we are looking at three steps. First is focusing on strengthening the mechanical properties of the material through cross-linking. For our ugly working prototype, our chemical makeup consisted of a base polymer of PEO and chitosan. These materials were dissolved in acetic acid and then spun as a solution. The Zwitter ions and the phenol red were both incorporated into the material before electrospinning. As shown in Figure 2, we have a regular mat, and then Figure 3 and Figure 4 separately show a phenol red mat and a Zwitterionic mat. All of these mats were mechanically unstable and dissolved in water within seconds. In order to address these mechanical issues, for our final product, we swapped out acetic acid for citric acid. This allowed us to cross-link our material through post-modification. Our electrospun mat was dehydrated for 24 hours in 40 degrees Celsius and then cross-linked for 10 minutes at 140 degrees Celsius. Additionally, Zwitter ions and phenol red were both attached to nanoparticles and sprayed onto the mat after cross-linking. This was done so that the particles would not be damaged by the heat, and will be further discussed in the section focusing on nanoparticle incorporation. In Figure 5, it is plain to see that the mat shrinks in size throughout post-modification and becomes a darker brown. There was no scale bar associated with these images, as these were pictures taken for our own documentation. Due to the coronavirus epidemic, proper images with scale bars were not able to be taken. After strengthening the mechanical properties, we tested to make sure that cross-linking had indeed occurred. Since the material had turned brown and stiff after post-modification, it was important to check the FTIR results to see whether the material was properly cross-linked or it had been burned during the cross-linking process. We did this by comparing our FTIR results with that found in the literature. FTIR results in literature predict that as dehydration occurs, the bonds break and the percent transmittance would decrease. As the material was then cross-linked and new bonds formed, the percent transmittance should increase. This can be seen as the percent transmittance decreases from the control shown in red to the dehydrated mat shown in green, and then increases as it is cross-linked from the green to the blue. Finally, we wanted to test the mechanical properties. We were only able to cross-link pieces of the mat which often shrank and would not fit into the Instron machine. Our plan after spring break was to cross-link an entire mat and then Instron test it, as a larger sample would fit into the machine. However, due to the coronavirus epidemic, we were not able to accomplish this. We would like to note, however, that the cross-link material was brittle when dry, but when placed in water was hard to rip with our fingers. We suspended the mat in water and it did not dissolve within 7 days, whereas before cross-linking, the material dissolved within seconds. Thus, we can expect that the mechanical properties of our material would have been sufficient given our expected results of it being up to 90% as strong under tensile force as a piece of standard gauze.
The next section of our project was the nanoparticle fabrication and application of the nanoparticles. This was a 4-step process, the first of which was synthesizing Zwitterionic nanoparticles. For the synthesis of our Zwitterionic nanoparticles, we adhered sulfobutane to the surface of silica nanoparticles. The purpose of this was to prevent biofilm adhesion in the wound. In this process, bacteria accumulate in a wound, but if the application of Zwitterionic nanoparticles, the charged layer forms a hydration layer that repels bacteria from adhering. The second step of our nanoparticle fabrication is the synthesis of phenol red doped nanoparticles. In this process, we create color-changing nanoparticles by synthesizing silica nanoparticles doped with phenol red. Through this process, we will be able to detect wound infection as phenol red nanoparticles will visually appear yellow and slightly acidic, indicative of a healthy wound environment, and will visually appear red when in a slightly basic environment, indicative of an infected wound environment. The third step of our nanoparticle application is spray coating them onto the bandage. We do this with an airbrush for application precision and so that we know the concentration of each set of nanoparticles applied. This also benefits the bandage because Zwitterions are not harmed in post-processing heat treatment required to cross-link the bandage. The final step of our nanoparticle fabrication is evaluating the nanoparticles on the bandage. We do this through a combination of FTIR spectroscopy to confirm the presence of the nanoparticles on the bandage, scanning electron microscopy, which characterizes the particles on the bandage, and pH testing, which will confirm the color change. Unfortunately, due to the coronavirus, we were unable to test scanning electron microscopy and pH testing. For the analysis of our FTIR results for the Zwitterion in the bandage, we were able to determine the Zwitterion was in the bandage. As you can see from these highlighted peaks, the nanoparticles in solution create distinct peaks on the wavelength scale. Compared to the spray-coated mat in blue, these peaks are present, versus the red control mat did not have these peaks present. For our color-changing indicator, we had previously prepared a pH solution slightly acidic of 6.5 and a slightly basic pH solution of 8.5. Had we had the time, we would have incubated nanoparticles in both the acidic solution and the basic solution and expected to see a color change to yellow in the slightly acidic solution corresponding to a healthy wound environment, and a color change to red in the basic environment indicative of an infected wound environment.
Future plans of ChitoAid consist of validating each feature of the bandage through cytotoxicity and bacterial testing. We would further perform Instron tests to analyze the mechanical stability of the bandage and then test for cytotoxicity with mammalian cells. We expect to see minimal to no shearing in the bandage as is desired when in contact with wounds, and we expect to see that at least 70% of the original population of mammalian cells survive. We would perform SEM to ensure that nanoparticles adhere to the bandage and test the antibacterial and pH sensor properties of nanoparticles by introducing E. coli to the bandage. We expect to see a major amount of bacterial death of at least 90% of the original population, and we expect to see an observable pH change from the presence of bacteria. Thank you for listening.